Everyone, the notes that I handed you in the last class for homework are a description of capacitors and their properties, and we're going to get into that in a second. But before we do that, I want to actually sort of review a little bit of our discussion last school year on conductors. So, of course, when I think of a conductor, I think of a metal. And one of the things I want to talk about are the properties of conductors. So let's just sort of lay that out quickly. I don't want to talk about every property of conductors, just two necessary ones. So conductors um, are basically a model for metals. Okay, and the rule for conductors is charges are absolutely free to move on conductors, but they can't leave the surface unless, and this will be our third point, they the surface of the conductor is connected to a wire. Okay. So I'll sort of explain some interesting properties of conductors like this. So maybe I have a rod made of plastic and I've managed to put some positive charge on that rod. So for example, let me just redraw this. So I have like a plastic rod. We'll draw it like this. We'll put some positive charges on it. And if I bring a conductor near it, here's what's going to happen. What's going to happen is that this completely neutral conductor that has a perfect mix of positive and negative charges, well, the charges are free to move on the conductor, but they're not going to leave the surface. So what happens is that the opposite charges on that conductor see these positive charges here, and it's like they all line up to want to be close to that surface, and then all these positive charges kind of get pushed to the other side like that. So you have these negative charges trying to jump off the conductor onto this charged rod here, but again, they're trapped on the surface. Now, here's an interesting thing that can happen, is that if I hook up this thing to what's called the ground, and I literally mean you connect it to the earth, these positive charges will actually go into the ground. They'll try to escape off the thing, and they'll just run away because the positive charges hold the negative charges onto the conductor. So the negative charges are held on the conductor, the positive charges kind of run into the ground, and then when I disconnect this, we'll end up having just a negatively charged sphere at the end. That's a little bit complicated. I think the way it's actually better to explain it, rather than using this argument here, is to talk about a system that consists of two conducting plates. That's our capacitor system right here. So the way we draw capacitors in AP Physics is like this. And our goal in this lecture is to introduce some of the fundamental physics of E&M by describing how capacitors work. We're going to introduce some of the fundamental physics of magnetism by talking about inductors. So just to be clear, we're introducing just capacitors and their properties right now to sort of zero in on one of the circuit elements we've studied. We're going to learn all of the physics of how capacitors work, and that's going to completely give us a knowledge of every bit of electricity that we need to know for the AP exam. After that, we're going to look at inductors and how they work, and we'll know everything we need to know about magnetism. So the month of March is going to be capacitors and their properties. The month of April is going to be inductors and their properties. And by the time May rolls around, we'll have everything we need for both the mechanics and the E&M AP exams. So let's get into how capacitors work. A capacitor, for our purposes, consists of two conducting plates. So remember, we're actually driving positive charge onto the plate on the left because we're hooked up to a battery, presumably. Now, what's going to happen is this, and you know what I should say is that we have some kind of battery right here. So we'll make this the positive end and this the negative end. And the idea here is that doesn't actually mean there's a positive or negative charge in the battery. We're just saying that that's where the charge comes out of. So not even comes out of, the battery doesn't create charge. This is how the charge is moved by the battery. So what happens is that this battery moves positive charge onto this plate here. And what happens is this positive charge attracts negative charge here. And it repels the positive charge in this other plate. Now, because that is connected to a wire, what ends up happening is that's how current gets driven around the battery. So what happens is you get a net accumulation of positive charge here, a net accumulation of negative charge. So let's be clear. There's actually positive charge on this plate, negative charge on the other plate, and sorry about that. So there's actually positive charge on this plate, negative charge on this plate. The overall charge on the capacitor is technically neutral. So when we actually talk about capacitors having a charge Q, what we're really saying is the total charge is 0, but there's plus Q on one plate and negative Q on the other plate. And that's what we're actually tracking, is sort of the absolute value of the charge on one plate. Now, here's what you need to know for the AP test. A capacitor consists of two plates. There's a positive charge on one plate, a negative Q on the other plate. The distance separating the plates are denoted as D, and each plate has an area denoted by A. So all of this are the facts that you should actually memorize about capacitors. And now we're going to get a little bit into some numbers, okay? So we'll call the plate area A. The plate distance, meaning the distance between these two plates, is called D. There's a charge in the positive plate equal to plus Q. The negative plate has an equal and opposite charge, negative Q. And we're going to define the surface charge density here on this capacitor as the charge divided by the area. That's a number that we make up. And this is a number that we actually used last year very briefly. So a quick review. We talked about the electrical force between two charges as being K, Q1, Q2 over R squared last year. And very briefly, we talked about the fact that yes, K has a value of 9 times 10 to the 9th newtons meter squared over coulomb squared. We also talked about the fact that K itself can be rewritten as a constant 1 over 4 pi epsilon naught. Once again, why we do this goes way back into the history of the units used in E&M. Sadly, E&M units are very, very annoying. So I just want you to note that there is a new constant that we introduced that has to do with how electricity behaves, and that's this constant right here. The analogy to think of is that we have G, which is 6.67 times 10 to the negative 11th, and that's kilograms squared, that's newtons meters squared over kilograms squared. This is sort of the fundamental constant for gravity that the universe uses for all its gravity related stuff. This is kind of the fundamental constant for electricity. Okay. Now, here are some facts that we need to get clear on. These are just facts that we're going to state for now. So these are all facts that we are going to prove later. Okay? So the first fact, 1 and 2, we're going to prove these later. For now, please memorize, though, that the field in between these plates is always uniform. And the electric field between these plates, okay, is defined as this quantity here. And here's the analogy that we're going to draw. So, in gravity physics, we have the equation F equals m times g, where g is the gravitational strength. And basically you take mass, times it by gravity, and it gives you a force. Here what we're saying is that the electrical force on a charged particle depends on the charge of the particle, and we're going to multiply it by this thing called the electric field. Now, on Earth, G is equal to 10 meters per second squared, and if you go back to our Kepler unit, that's going to be G, mass of the Earth, divided by the radius of the Earth squared. So the idea is that we want to measure the gravitational force. We take the mass of the object that's affected, and then we multiply it by this constant here that has to do with Earth's mass and its radius and the gravitational constant. What we're doing here is constructing an analogy. We're saying that there's an electrical force on any charge in between these plates, and that electrical force is equal to the charge times the electrical strength. We call the electrical strength the electrical field in physics. And basically what we're saying is, by analogy, Fg equals mg, Fe, the electrical force, equals the charge times the electrical field. Now, for a parallel plate capacitor, this is simply the formula to memorize for now. Okay? We are going to prove this formula after we learn a few mathematical tools for calculating electric fields. We're just not going to do that today. So for our purposes, the electric field is simply the charge divided by the area of the plates, which is the density of charge. And then we're going to divide that by the electrical constant, epsilon naught, which is 8.85 times 10 to the negative 12. So, to summarize everything that we need to know for AP Physics for capacitors, a capacitor consists of two plates. When you charge it up in a circuit, the left plate's going to get a charge plus Q, the right plate is going to get a charge negative Q, that's assuming the battery's hooked up like this. So the overall charge on the plate is 0. Okay, so that's kind of the first point right here. Next, the distance separating the plates is denoted as D. The area of the plate is denoted by A. And so yes, the net charge of the capacitor is 0, but we always refer to the charge on the capacitor by referring to the positive plate charge, which is what we did in circuit theory. Now, what we're interested in doing is getting into the fundamentals of how capacitors behave. So in between these two capacitor plates is an electric field that works very much the way a gravity field does on mass. So the way gravity fields attract mass is that they exert a force on them. The way electric fields affect charges is that they create a force on electric charges. And so the idea here is, just as gravity is m times g, force of gravity is m times g, the force of electricity is charge times E. The one thing that we need to memorize, though, in terms of math, is this is the formula for the electric field in between the plates of a capacitor. Why this is true, we're going to learn later on. So, again, electric field between a capacitor is uniform. The left plate has a charge plus Q, the right plate has a charge negative Q. These are the relevant numbers for capacitors. The electric field is sigma over epsilon naught, which is the surface charge density divided by epsilon naught. This is a formula to be memorized and used for now, which we will prove later. And the force on a charged particle given by F equals Q times E. We're going to apply these formulas a little bit in our next video.